Jai Hind, welcome to class of Fundamentals of Electronics Engineering. We are talking about digital electronics and introduction to them. So these are the contents. We'll be talking about number system and its representation, introduction to Boolean, algebra, basic universal gates, simplification of Boolean function, K-map, minimization up to 6 variable. So, what are logic gates? What do we mean by number system? It was developed by English mathematician George Boole in between 1815 and 1864. It is described as an algebra of logic or an algebra of two values, that is true or false. The term logic means a statement having binary decision, that is false or no, true or yes. We can think of a logic as a switch for a bulb, which closes when we switch on it, right? So it is true or on when the binary input is 1, and it is false or no when the binary input is 0. Applications of Boolean algebra. It is used to perform the logical operations in digital computer. So we can think of logical gates or Boolean algebra as basics of any digital device. So these are used for logical operations in digital computers, devices like smartphones, tablets, etc. And digital computer, true represents 1 or high volt and false represents low volt. Logical operations are performed using logical operators, and these logical operators are, these are my three basic logical operators, and which is also called as conjunction, or which is also called as disjunction, and not, which is negation or complement. If I talk about the AND operator, it performs logical multiplication and it is denoted by dot. So these are my two binary inputs x and y, and x dot y will give me AND operation. So if I have two binary inputs, then number of possible outcomes will be 4. How do we go by it? I know number of binary bits 2. So number of possible outcomes will be 2 to the power n, which comes here to be 4. And the possibilities are my 0, 0, 0, 1, 1, 0 and 1, 1. So these are the possible inputs that I can provide using 2-bit binary input. So for 0, 0, if I go with the multiplication, it will give me 0. 0, 1 will give me 0 again. It will only give me 1 when both the inputs are 1. So this is how my AND operator works. If I talk about OR operator, then either of the input is 1, then I do get 1 output. So there is the possibility of obtaining 0 only when both the inputs are 0. So logical operation or which is represented by plus, right? As I earlier discussed, that if there are 2-bit binary input, then number of possible outcomes will be 4, corresponding to 0, 0, 0, 1, 1, 0 and 1, 1. So as it is OR operation, which is logical addition, hence 0, 0 will give you 0, 0 plus 1 will give us 1, 1 plus 0 gives us 1, and 1 plus 1 gives us 1. This is how my binary operation works. 1 plus 1 is always 1, because this is the highest possible outcome. I do have two kinds of outcome, that is either 0 or 1. 0 is the false, that is minimum, 1 is the maximum, or we can say high or low. So these are the possible outcomes. NOT operator acts as a negation, that is it performs the inverse operation. If I provide input 0, output I'll get is 1. If I provide input 1, I'll get output as 0. It performs logical negation and is denoted by this bar. It operates on single variable, right? there should be one input to apply NOT operation. We can call X bar as complement of X as well. What is truth table? A truth table is a table that contains all the possible values of logical statements. Right? So, number of possible combinations is given by 2 to the power n, where n is the number of variables used in a Boolean expression. Now let us talk about, let's practice making some truth tables. Like if I want to make truth table for x into y plus z, how do I make it? I get to see here I have 3 variables, x, y and z. So by this I am writing the sequence here, right? And with x, y, z I am writing 3 inputs. What I have to perform is x into y plus z. So I'll do x into y in the first step. In the second step, what I'll do, I'll add the value of z in x plus y, which I write here, right? Now as here I have 3 variables, so I have n equals to 3. The number of possible outcomes will be 2 to the power n, which is 2 to the power 3 equals to 8, right? So that corresponds to 000, 001, 010, 011, 100, 101, 110 and 111. These are my 8 possible input combinations that can be applied to a device that will follow this logical operation. So let us see what will be the value of x into y. As discussed before, x into y is logical multiplication. So we'll simply check these 2 inputs for this column, right? 0 into 0 is 0, 0 into 0 is 0, 0 into 1 is 0. It will be 1 only in case where x and y both are 1. So we'll check for where do we have x and y both 1. So in these last two rows. So here I put 1, rest all 0. The next step is to make addition with the z. Addition of what? X into y. So we'll check this column and this column, and output this will be addition of these, right? So when this is logical addition, addition will be 1 wherever there is even single 1, otherwise it is 0. So 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1 and 1 plus 1 is 1. So this is how I can make truth table for the desired logical argument. What is tautology? If the output is always true, we call it tautology, and if it is false, then we call it fallacy. Right? These are few questions that can be performed, that can be practiced. Now let's talk about the implementation. Now Boolean algebra applied in computers, electronic circuits. It is always applied in electronic circuits. These circuits perform Boolean operations and these are called as logical circuits or logical gates. Why these are called as logical circuits or logical gates? Because they operate based on, their operation is based on certain logic. What is a gate? You might have heard of the term logical gate or logic gates. A logic gate is a device, or it is a digital circuit which operates on one or more signals that produce single output. These are my basic logical gates. Basic logic gates. These 3 are my, although I have 7 logic gates, out of those 7, these 3 are my basic logic gates. And, or and not gate. Gates are my digital circuits because their input and output signals are denoted by either 1 or low, 1 or 0. There are 3 basic gates: AND, OR and NOR. Let's talk about AND gate. As the name suggests, AND gate, it is based on the logical operation, which is mathematical multiplication. AND gate takes 2 or more input and produces 1 output. AND gate is an electronic circuit that gives a high only if all of its inputs are high, because a logical multiplication, 1 into 1 will give you 1, 1 into 0 will always give you 0. So this is how we draw the symbol for AND gate, right? With 2 inputs, we have denoted these as A and B, and the output can be denoted as A into B. So I have written AB. So this is the representation for AND gate. And if I want to draw the truth table for it, so I'll have to draw 2 columns for the input, that is input A, input B, and output will be A into B. So 0, 0 will give you 0. So everywhere it will be 0 apart from the row where both the inputs are 1. Here, rest 0, right? Because AND operation, logical multiplication. Output is high only when all the inputs are high. OR gate. Let's talk about OR gate. It operates on mathematical addition. It gives a high output if one or more of its input are high. OR gate takes 2 or more input signal and produces only 1 output signal. This is how we represent OR gate. This is a simple representation. Provide 2 input, 1 output. A and B are input, and A plus B represents logical OR. If I talk about the truth table, I'll have to draw 2 inputs and 1 output, that is A plus B. So it will have 1 output everywhere apart from where both the inputs are 0. Otherwise, all ones. Logical addition. You can see 0 plus 0 is 0. Otherwise, 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. NOT gate. The NOT gate is an electronic circuit that gives a high output if its input is low. NOT gate takes only 1 input signal and produces only 1 output signal. The output of NOT gate is complement of its input. As discussed earlier, it is also called as inverter. So it will have only 1 input and output will be inverse of it. This is how it is represented. A triangle, a circle in front of a triangle. 1 input, 1 output. If the input is A, output is A bar. If the input is B, output is B bar. How do I draw the truth table for it? For 0, output is 1. For 1, output is 0. Now what are the practical applications of logic gates? Now think of an AND gate. Like, can you think of a burglar alarm which is on only when both the inputs are on? So we have a person sensor and an alarm switch, and it will ring only when both the inputs are on. If both the person sensor and the alarm switch are on, then the burglar alarm is activated, right? So while going out of the house, you set the alarm switch, and if the burglar enters, he will set the person switch and tada, the alarm will ring, right? While we go out, we make alarm switch as 1. And the person switch will only be 1 when some thief enters the house, and when he enters, it will ring. Electronic door will only open if it detects a person and then the switch is set to be unlocked. We have made the logic like door will be open. There is one continuous one and another one only when there is a person. So when there is the presence of a person, the sensor will detect it as 1 and the door will open. Microwave will only start if the start button is pressed and the door closed. When does my microwave works? If the door is open and if I turn on it, it will not be turned on. There are two conditions for it. Both has to be satisfied. That is, the door has to be closed and I have to turn on the start button. When these two conditions are present, that is logical 1, then only microwave will start. If I talk about the practical applications of logic gates, front doorbell switch, back doorbell switch. Either of these two, in presence of either of these two conditions, the doorbell should be ringing, right? Either I press the front doorbell or the back doorbell, right? So this is where we can use OR gates. You would of course want your doorbell to ring when someone presses either the front door switch or the back door switch, right? Now if I talk about the NOT gate, my NOT gate, no human, off. Human is present, central heating on, right? So vice versa is the operation. If the temperature is above 20 degree Celsius, then the central heating is switched off. If the temperature is below 20 degree, so here we have set a threshold of 20 degrees Celsius, right? And inverse to it, the operation is working. When the temperature falls below 20 degrees Celsius, the NOT gate will set on the central heating system. These are rest 4 gates. Like earlier I mentioned, we have 7 gates. Out of the 7 gates, 3 basic gates we have just studied. These are rest of the 4 gates: NAND, NOR, XOR and XNOR gate. What is a NAND gate? NAND gate is a universal gate. Actually, we'll get to see in our coming slides that NAND and NOR, these are our 2 universal gates. So it is a universal gate. Why do we call it universal gate? Because any of the gate can be constructed using NAND gate. How do we make a NAND? We put a dot, we put a circle in front of AND, and this will give us output which is inverse of AND, right? We know in AND, when both the inputs are on, we get 1. So in NAND, when both the input are 1, we get 0, and other than this, we get all ones. Isn't it inverse of AND? Right? So this is how I can make the truth table for NAND gate. This is how other gates can be constructed. If I want to make a NOT gate from a NAND gate, how do I make? I have to combine the inputs, because I know that AND will have 2 inputs, whereas a NOT gate has just 1 input. So to make the input common, I do this thing. So when X is the input, I should be getting X bar as output. So let's check. I have what is this? I have to perform AND operation first, then complement it, then it will give me NAND, right? So X dot X is AND, and this symbol represents complement, or it is equivalent to either I write this or I write this. It's one and the same thing, right? It means the complement. So AND operation is X dot X, and X dot X bar is inverse of it, which is NAND, right? So using De Morgan's law, I know that A dot A whole bar is A bar plus A bar, and we know that 1 plus 1 is always 1, or A plus A is A. So what do I get? X bar. Input was X, output is X bar, which is the logical operation followed by NOT gate, right? Hence I can make a NOT gate using a NAND gate. If I talk about AND gate, can I make an AND gate using NAND gate? Yes. With the help of 2 NAND gates, you can obtain the output which is similar to AND gate. So if the two inputs are x and y, my NAND gate will give some output. Then when you combine that input and provide it as common input to next NAND gate, first NAND gate, second NAND gate, and the output will be equal to AND gate. How? Let's check it here. This is x dot x bar. Now what is happening here? Double bar, right? So when I open this double bar, what do I get? When I open this outer bar, using De Morgan's law, I do get as x bar plus y bar. So not the outer bar, let's open this inner bar first. When I open this, I do get as x bar plus y bar, and outside this square bracket, round bracket, I do have this bar. Now again open it, I do get x double bar dot y double bar using De Morgan's law. It converts plus into multiplication, multiplication into plus, right? What does De Morgan's law says? Right. So double bar gives you the same component. So here the output comes out to be x dot y, which is AND. Similarly, we can make an OR gate from this with the help of 3 NAND gates. How? To the first NAND gate, combine the input. What do we get here is x bar as used from the first operation. Here what do we get? Y bar, and x bar dot y bar whole bar. X bar dot y bar whole bar will give you x plus y. This is how we get OR output. That is, using 3 NAND gate we can make an OR gate, right? Likewise, it is represented here itself, right? So this is stepwise representation. This combining output gives you output equal to NOT gate. Here it is replaced by 2 NOT gate, and we get what is desired. If I talk about NOR gate is represented first by OR, then putting a circle in front of OR. So whatever an OR gives, the inverse of it will be the output of NOR gate. So in OR gate we know input is always high when either of the input is high. Here when either of the input is high, it will be low, that is inverse of it, and it is high when both the inputs are low. So this is how NOR works. Exclusive OR gate. What is exclusive OR? XOR. XOR can be drawn by making an OR first, then this is how the symbol looks like. 2 input, 1 output. XOR will have 0 output when both the inputs are similar, and in case of dissimilar input it will have 1 output. Now next is exclusive NOR. So we have to draw NOR first, then the symbol. In case of XNOR, the output is 1 when both the inputs are similar, and in case of dissimilar input, the output is 0. That's all for today, and these are the references that I have used. Thank you.